Good morning, everyone. First of all, I appreciate the organization committee for giving me such a great opportunity to represent my results at this conference. My report is going to be about primary radical cations in irradiated liquid solutions of tetrahydrofuran and its further transformations. Deprotonation of radical cation is a very probable pathway of transformation of radical cations. In particular, it was typically believed that in case of ethers, deprotonation proceeds in picosecond time domain. As you can see at the picture, As you can see in the picture, the results of experiments that was made by Martini and others. At this chart, the signal of the optical absorption of radical cation of THF decrease after the 2 picoseconds after its formation. At the constant level of the signal at the wavelength that corresponds to the absorption of electron. There are studies of the products of this reaction which are stabilized in matrices at the low temperature, but there are no such works that this radical cation is studied in liquid solution at the own neighbor. In the figure, you can see experimental setup for obtaining recombination luminescence of spin-correlated pairs. It consists of several parts. First of all, there is an X-ray source with photon energy about 12 kilo-electron volts. Then there is a sample tube which is being irradiated. Next, there is a 2 Tesla magnet with negative feedback stabilization system for zero field. And the main part is the fluorescence measurement apparatus, which main part is single photon counting unit, which main part is photomultiplier element. Temporal resolution of kinetics is about 2 nanoseconds. We managed to register the radiation-induced recombination fluorescence of solvent molecules in liquid tetrahydrofuran. The fluorescence is quenched by an electric field, as you can see in this picture. As well, we observe magnetic field effect on fluorescence. There is a black curve. The time-resolved magnetic field effect is a ratio of kinetics of fluorescence in high magnetic field to the kinetics of fluorescence in zero magnetic field. We also observe effect of full deterioration of tetrahydrofuran. So what are these oscillations that you can see on the chart? Let's say a few words about them. Spin-correlated pairs are formed by ionization of the molecule, and the total electron spin is not changed while the process of ionization. Quantum bits occur in any system in which the state is coherent superposition of stationary states. In the simplest case, which you can see as the Formula 1, there is a superposition of stationary states A and B. So the state at any given moment will behave such way as in Formula 2. And if we have a value x that is not directly dependent on time, the mean value have such constant, and it will be oscillate with a frequency that is proportional to the differences of the energies. The nature of such oscillations is the difference between G factors and hyperfine constants with unpaired electron. The observed range of the quantum bits in magnetic effect carries information about the constants of hyperfine interactions, but we cannot obtain it directly from our magnetic field effect. But we could simulate it with a range of hyperfine constants. First of all, we tried to simulate in the case that radical cation of tetrahydrofuran is not decay, but we cannot obtain good agreement with our experiment data. So then we made a simulation for radical cation of our fluorescence addition para-terphenyl fully deuterated, but there is also no agreement. To clarify the structure of the observed particles, quantum chemical calculations were made. We have used density functional theory. We use a set of functionals M06 to X, and we also use polarizable continuum model to take into account the solution. The calculations show that our system has extremely complicated potential energy surface with a lot of transitional states and local minima. There are two of structures that corresponds to the minimas. The first has shifted proton between two oxygens. We call this complex OHO. And the second structure has direct bond between oxygens. We called it OO complex. We calculated relative energies that you can see at the table, but we have problems with calculation energy of system with full separation, cation and radical. We could reasonably simulate the curves of time-resolved magnetic field effect using two different assumptions. The first assumption is that primary radical cation of THF is transformed into the radical cation of dihydrofuran due to very fast hydrogen elimination. The simulation for this case is shown by the blue line in the upper part of chart. The second assumption is that weakly bound diastonic dimers stabilized by hydrogen bonds between the radical cation of THF and molecule are formed. According to the quantum chemical calculation, there are two types of such dimer, but none of them by itself can make a good agreement with our experiment data. So we have assumptions that there are two of such complex of dimers in our solution. But in all of that case, we don't have the best agreement. And after all, we made the assumption that one of the complexes decay in the tens of nanoseconds. So we get our best agreement with theory, but the constants of calculations are uncertain. So I'd like to conclude. It was shown that irradiation of para-terphenyl solutions in tetrahydrofuran causes recombination fluorescence, which is quenched by an electric field. We also observed the magnetic field effect that affects on our kinetics of fluorescence, and we also observed the effect of deuteration to the magnetic field effect. In solution, there is a particle or a few particles stabilized with times about tens of nanoseconds, carrying a charge and having an unpaired electron. Thank you for your attention.
Is the oxygen-oxygen bonding a 3-electron bonding?
No. There is a quantum chemical calculation, so I question about the origin of this bond.
Yes? Okay. I have the answer. Thank you.
Okay, we move to our last speaker of this session, and this is